So, think about the sheer variety of sounds that make up our daily lives. That morning alarm jolting you awake, maybe the comforting murmur of a friend's voice, the distant wail of a siren, or, the intricate melodies in your favorite music. What's truly fascinating is that every single one of these originates from the same fundamental phenomenon: vibration. Something, somewhere, is shaking.
That really is the key, isn't it? And, well, this deep dive is all about unpacking that fundamental idea. Vibration and how it transforms into the energy we perceive as sound. We've gathered some really insightful material that breaks down how sound waves travel, what they absolutely need to travel through, and even explore the hidden world of sounds beyond our normal hearing range.
Exactly. Our goal today is to truly understand the essence of sound waves using these resources. We'll be digging into why they can't exist in empty space, how their speed changes depending on what they're moving through, and the, well, surprising characteristics of infrasonic, sonic, and ultrasonic frequencies. Okay, so let's start at the very beginning. Where does sound actually come from?
Right. At its core, sound is born from vibration.
Yeah.
Every sound you've ever heard started with an object physically vibrating,
Huh.
disturbing its immediate surroundings. Our sources illustrate this really beautifully with several kind of foundational experiments.
Right. Think about plucking a guitar string. You can literally see it moving back and forth, can't you? And you hear the note. That visible wobble is directly linked to the sound. And then there's the classic tuning fork. Strike one of those, and if you hold it near a tiny ping pong ball hanging by a thread,
Oh yeah, the ping pong ball experiment.
you'll see it dance wildly. It's proof that even invisible vibrations are creating a force, and, well, thus, sound.
Exactly. And this principle, it extends beyond musical instruments. Consider a drum. When you hit the skin, you can see the surface vibrating, and that's what produces the sound we hear resonating. Even something as simple as blowing across the top of a bottle causes the air column inside to vibrate, generating a tone. Experiments 1 through 5 in our materials clearly demonstrate this fundamental link. No vibration, absolutely no sound. It's this mechanical agitation that creates the initial disturbance.
So, okay, these vibrations create a disturbance that then travels outward. But what exactly is being sent out? This brings us to why sound needs a highway, as we put it.
Precisely. The vibrating object doesn't just, beam sound directly into your ear. It needs a material medium to carry that disturbance. Sound propagates as mechanical energy, a wave that travels through the particles of matter, bumping into each other and transferring that energy along.
And the iconic demonstration of this necessity is the bell jar experiment, isn't it? Can you walk us through that?
Ah, yes. Experiment 6. Figure 8.4 in our resources shows it perfectly. An electric bell is placed inside a sealed glass jar that's connected to a vacuum pump. When the bell rings with air inside the jar, the sound is easily audible. Clear as, well, a bell. However, as the vacuum pump removes the air, the sound gradually fades away. Eventually, even though you can still see the bell's hammer striking the gong, you hear next to nothing.
That fading into silence really underscores the point, doesn't it? It's quite dramatic. So what are the crucial characteristics that this highway, this medium, must possess to allow sound to travel?
Well, for sound to travel effectively, the medium needs a couple of key things. First, elasticity. That means its particles have the ability to return to their original positions after being disturbed. Think of it like a spring. It also needs inertia, which is the tendency of those particles to resist changes in their motion and to store and transfer the mechanical energy of the sound wave. Ideally, the medium should also have minimal internal friction to prevent the sound energy from being lost as heat while it travels.
So air, water, and even solid steel act as mediums for sound because they have these properties, elasticity and inertia. But then we have materials like thick blankets or soundproofing foam, which seem to block sound. How does that fit in?
Exactly. Materials like air, water, and steel readily transmit sound because their particles can effectively interact and pass along the vibrational energy. They're good highways. On the other hand, sound-absorbing materials like blankets and foam are, well, designed differently. They're designed to dampen these vibrations, converting the sound energy into other forms, like a tiny bit of heat, rather than allowing it to propagate through easily. They sort of soak it up.
Gotcha. And what about the complete absence of a medium, like space?
That's a vacuum, like the near-empty space in our bell jar experiment, or the vast emptiness between planets. As the bell jar experiment clearly shows, without a medium, without those particles to bump into each other, sound simply cannot travel. Zero highway.
Which is why astronauts on the moon can't just talk to each other normally.
Precisely. They need radios, even if they're standing side by side. It's a stark contrast to light, which as our sources remind us, has no trouble at all zipping through the vacuum of space. Light doesn't need the highway.
Okay, so sound needs a medium, and it travels in the form of waves. But what kind of waves are we actually talking about? Time for a little wave science.
Right, so when a sound source, like, say, that vibrating metal strip in figure 8.5, creates a disturbance, that disturbance propagates outward through the medium as a wave. In air, and actually also within liquids and solids, sound primarily travels as longitudinal waves.
Longitudinal. Okay, let's break that down. What does that mean for the individual particles within the medium? How are they moving?
Good question. In a longitudinal wave, the particles of the medium oscillate back and forth in the same direction that the wave itself is traveling. Imagine a slinky toy lying flat on a table. If you push one end forward sharply, you create a compression, the coils bunch up, right?
I can picture that.
This compression travels down the slinky. And when that compressed section moves forward, it leaves behind an area where the coils are more spread out. That's a rarefaction. Sound in air is basically a continuous series of these compressions, where air molecules are forced closer together, higher density, higher pressure, followed by rarefactions where they spread out, lower density, lower pressure. And this whole pattern moves in the same direction as the sound itself.
So it's like a pulse of high and low pressure rippling through the air. Okay. Now, our notes also mention transverse waves. How are those different?
Right. Transverse waves are different. They're illustrated by, say, ripples on the surface of water in figures 8.6 and 8.7. In these waves, the particles of the medium move up and down, or side to side, perpendicular to the direction the wave is traveling. Think about a cork floating on water when a ripple passes by. The cork just bobs up and down, right?
Yeah, it doesn't travel across the pond with the wave.
Exactly. The wave moves horizontally, but the cork, the particle, moves vertically. That's transverse motion.
So compressions and rarefactions for longitudinal waves, like sound and air, and crests and troughs for transverse waves, like light or water ripples. Where do we encounter transverse sound waves then? Or do we?
Good point. Transverse waves can occur in solids, like vibrations traveling through a rigid bar and on the surfaces of liquids. But they generally don't travel within the bulk of liquids or in gases. The sound that travels through the air to reach your ears, that's fundamentally a longitudinal wave.
Got it. Longitudinal for sound and air. And are there any general characteristics that all waves, both longitudinal and transverse, share?
Yes, definitely. Regardless of their specific type, all waves are generated by some kind of repeating or periodic disturbance within a medium. And crucially, they act as carriers of energy. They transfer that energy from one point to another without any overall net movement of the medium's particles themselves. The individual particles just oscillate around their average positions, passing the energy along to their neighbors, kind of like a bucket brigade.
Okay, we're talking about waves, so there's a specific vocabulary that comes with them. Let's decode some of these key terms. First up, amplitude. What's that?
Amplitude is the maximum displacement, or distance. A particle in the medium moves from its undisturbed resting position as a wave passes. It essentially tells you how intense the vibration is. Its standard unit of measurement is the meter. You can think of it as the height of a wave's crest or the depth of its trough in a transverse wave. For a longitudinal wave, it relates to how much the medium is compressed or rarefied.
And a larger amplitude generally means a louder sound, right?
Generally speaking, yes. Amplitude is closely related to the energy the wave carries, which we perceive as loudness.
Okay. Next, we have time period.
The time period, usually represented by the symbol T, is simply the duration it takes for one complete cycle of vibration of a particle in the medium. Or you could think of it as the time it takes for one full wavelength to pass a specific point. Its SI unit is the second.
And directly related to that is frequency.
Precisely. Frequency, denoted by F, is the number of complete vibrations or wave cycles that occur in 1 second. Its SI unit is hertz, abbreviated hertz. 1 hertz equals 1 vibration per second. And what's really important here is that the frequency of a sound wave is determined solely by the frequency of the original vibrating source. It doesn't change as the sound travels through the medium.
And there's a mathematical link between frequency and time period.
Yep, a very simple one. Frequency is just the reciprocal of the time period, so 5 apple equals 1 $t. If the time period is long, the frequency is low, and vice versa.
Makes sense. Then we have wavelength.
Wavelength, symbolized by the Greek letter lambda, is the distance the wave travels during one complete time period, t. Alternatively, you could visualize it as the distance between two successive identical points on the wave. So from the center of one compression to the center of the next, or from one crest peak to the next crest peak. Its SI unit is also the meter.
And finally, wave velocity. How fast the wave is moving.
Right. Wave velocity, or wave speed, v, is the distance the wave travels in 1 second. It represents how quickly the energy of the disturbance propagates through the medium. The SI unit is, naturally, meters per second, and it's crucial to understand this. For a given medium under constant conditions, like temperature, the wave velocity is constant. It depends on the medium's properties, its elasticity and density, not on the properties of the wave itself, like frequency or amplitude.
Okay, so the medium dictates the speed. Our notes also mention displacement time and displacement distance graphs. What information do these visual tools give us?
Ah, yes. These are graphical ways to represent wave motion, which can be helpful. A displacement time graph, like figure 8.8, tracks the movement of a single particle in the medium over time as a wave passes through its location. On this graph, you can clearly see the amplitude, the maximum displacement, and the time for one full up and down or back and forth cycle.
Okay, that's one particle over time. What about the other graph?
The displacement distance graph, figure 8.9, is different. It offers a snapshot of the entire wave at a specific moment in time. It shows the displacement of all the particles along the wave's path at that instant. This graph allows you to visualize the amplitude again, but importantly, it also shows the wavelength, the spatial distance between repeating parts of the wave.
Got it. One shows time, the other shows space. Okay, so we've got a handle on the anatomy of sound waves now. How fast do these waves actually travel? It's not instantaneous, right?
Absolutely not. Sound travels at a definite measurable speed, and it's actually, well, quite slow compared to light. Think back to that distant blacksmith hammering metal example or thunder and lightning. You see the event before you hear it.
Right. That delay is proof.
The tiny delay proves that sound takes time to propagate from the source to your ears.
And what are the primary factors that determine the speed? You mentioned elasticity and density earlier.
That's exactly it. The speed of sound in a given medium is fundamentally governed by those two key properties.
Yeah. Its
elasticity, its resistance to deformation, and its density, its mass per unit volume. The general relationship is expressed by the formula Vince fracture: more elastic, faster speed; more dense, slower speed. Usually. It's the ratio that matters.
And E is different for solids and fluids.
Yes. For solid materials, E typically refers to Young's modulus. For fluids, that's liquids and gases, it's the bulk modulus, which measures resistance to compression.
Okay. Now, our sources discuss Newton's early attempt to calculate the speed of sound in a gas, specifically air. What was his thinking?
Newton made an assumption. He assumed that when sound waves travel through a gas, the compressions and rarefactions happen slowly enough that heat can flow, keeping the temperature constant. This is called an isothermal process. Based on this assumption and some gas laws, he derived the formula rho squared, where P is the pressure of the gas.
And how did his calculations stack up against reality?
Well, for air under standard conditions, his formula gave a speed of about 279.5 meters per second.
But the actual measured speed was higher.
That's right. Experiments showed the speed of sound in air was closer to 330 meters per second. A noticeable difference, about 15% off.
So Newton's isothermal assumption was flawed.
It turned out to be incorrect for sound waves. The compressions and rarefactions happen too quickly for heat to effectively transfer in and out. It highlights a crucial part of science testing theories against observation.
Okay, so who fixed it? Enter Laplace.
Exactly. Pierre-Simon Laplace proposed a correction. He argued that the process is actually adiabatic, meaning there's no significant heat exchange with the surroundings during these rapid pressure and volume changes. The temperature fluctuates locally within the wave. He introduced a correction factor, gamma, into the equation. Gamma is the ratio of the specific heat of the gas at constant pressure to its specific heat at constant volume. It's a property of the gas itself.
And the corrected formula.
The corrected formula became Visor gamma. For air, gamma is approximately 1.4. Plugging this value in gives a calculated speed of around 330.7 meters per second at standard conditions.
Much closer.
Much, much closer. It aligns very well with the experimental results, confirming that the adiabatic assumption is the correct one for sound propagation in gases. Science corrects itself.
So the speed of sound isn't the same everywhere. How does it generally compare in solids, liquids, and gases?
There's a clear trend. Sound travels fastest in solids, then slower in liquids, and slowest in gases, generally speaking. This is largely because solids tend to be much more elastic. They resist deformation more strongly and snap back quicker compared to liquids and gases. Even though solids are also denser, the elasticity factor usually wins out.
And we have some numbers for comparison.
Yeah, the table in our sources gives good examples. Approximately 5,100 meters per second in steel. That's really fast. Around 1,450 meters per second in water. And down to about 330 meters per second in air at 0 degrees Celsius.
Wow, that's a huge difference between steel and air, over 15 times faster. Our sources mention hearing a train through the tracks first. That makes perfect sense now.
Precisely. The vibrations from the train wheels travel much more efficiently and rapidly through the dense, highly elastic steel rails than they do through the much less dense and less elastic air. Another example given is if you strike one end of a very long steel bar. Someone at the other end would actually hear two distinct sounds.
Two sounds.
The first sound arrives very quickly, having traveled through the steel itself. The second sound arrives a bit later, having traveled through the air surrounding the bar. It's a direct consequence of that speed difference.
Fascinating. Okay, we've established the medium type is crucial. What about factors within a specific medium, like air? What influences how fast sound travels there?
Right, focusing on gases like air, several factors come into play. Density is one. The speed of sound is inversely proportional to the square root of the density. So, Vtroptofrac, Cartofrac, if you compare hydrogen gas and oxygen gas at the same temperature and pressure, hydrogen is much less dense, and sound travels significantly faster in hydrogen, almost 4 times faster, actually.
Okay, less dense, faster sound. What about temperature? Does sound travel faster on a hot day?
Yes, it absolutely does. Temperature has a direct impact. As the temperature of a gas increases, its molecules move faster and have more kinetic energy. This means they collide more frequently and energetically, allowing the sound wave that disturbance to propagate faster. The speed of sound in a gas is directly proportional to the square root of the absolute temperature, measured in Kelvin. So it's Frapta score.
Is there a simpler rule of thumb for air?
There is a convenient approximation for air near room temperature. For every 1 degree Celsius rise in temperature, the speed of sound increases by roughly 0.61 meters per second. The formula is VeV plus 0.61d, where V is the speed at 0 degrees C, about the 330 meters, is the temperature in Celsius. So yeah, sound is noticeably faster on a warm 25 degrees C day compared to freezing.
Interesting. Humidity was mentioned too. I wouldn't have guessed that.
Yeah, it's a bit counterintuitive perhaps, but humidity does have a subtle effect. Water vapor molecules, teach 2 other Zollers, are actually less massive than the main components of dry air, nitrogen 2 under 2 and oxygen 2 under 2. So when humidity increases, meaning there's more water vapor mixed in, the overall density of the air actually decreases slightly.
And lower density means faster speed.
Exactly. So sound travels marginally faster in humid air compared to dry air at the same temperature and pressure.
And wind direction, that seems more straightforward.
It's pretty much what you'd expect. If the wind is blowing in the same direction the sound is traveling, it effectively carries the sound wave along, increasing its speed relative to the ground or a stationary observer.
Like swimming with the current.
Precisely. And conversely, if the wind blows against the direction of sound propagation, it slows the sound down relative to the observer, like swimming against the current.
Okay. Now, are there factors that we might think would affect the speed of sound in a gas but actually don't? Things that turn out not to matter?
Yes, there are a few important ones to clarify. First, pressure. While pressure P appears in the formulas for an ideal gas, changing the pressure without changing the temperature doesn't affect the speed of sound.
How can that be? It's in the formula gas-Gahal.
Because when you change the pressure of a gas isothermally at constant temperature, its density changes in direct proportion. The ratio par remains constant, so the speed doesn't change.
Okay. The ratio stays the same. What else doesn't matter?
The amplitude of the sound wave. How loud or intense the sound is has no bearing on how fast it travels. A loud shout travels at the same speed as a quiet whisper in the same air.
Okay.
And finally, the wavelength or the frequency of the sound wave itself doesn't alter its speed in a given medium under constant conditions. A high-pitched note travels at the same speed as a low-pitched note.
So speed depends on the medium and its conditions, temperature, humidity, but not on the characteristics of the sound wave itself. Loudness, pitch.
That's the key takeaway for speed in a given medium, yes.
Okay, let's shift gears a bit now and compare sound to another fundamental form of energy we encounter constantly, light. How do they stack up?
Right. This is a really illuminating comparison, highlighting just how different they are. We've touched on some points already. Firstly, the big one, the medium. Light, as we said, is an electromagnetic wave and can travel perfectly happily through the vacuum of space. It needs no medium.
Whereas sound absolutely needs a medium. No medium, no sound.
Correct. Sound is a mechanical wave requiring particles to vibrate.
And the difference in their speeds is just astronomical, isn't it?
It really is. The speed of light in a vacuum is roughly 3 tallers times 10 meters per second. That's 300 million meters per second. It's incredibly fast.
And sound in air.
A comparatively snail-like 330 meters per second or so. Light is nearly 1 million times faster than sound in air.
Which is why we see lightning almost instantly, but the thunder takes seconds to arrive, even if it's from the same spot.
Exactly. That huge speed difference explains so many everyday phenomena. Think about a starter's gun at a track meet. The officials near the start line hear it instantly, but the runners further down the tracks see the smoke puff from the gun a fraction of a second before the sound reaches them.
Or watching baseball from the stands, you see the bat hit the ball, then hear the crack a moment later.
Perfect examples. It's all down to light's immense speed advantage.
Now, how do their speeds change when they enter different media? Is it the same pattern for both?
Nope, quite the opposite, actually. This is another key difference. Light generally slows down when it enters a denser optical medium. For instance, light travels slower in water or glass than it does in air or vacuum.
Okay, light slows down in denser stuff. What about sound?
Sound, as we discussed, generally travels faster in denser, more elastic media. It's faster in water than in air and much faster in steel than in water.
So they behave oppositely in that regard. Interesting.
Yes. Where light typically slows down in denser materials, sound typically speeds up, because the increased elasticity usually outweighs the increased density effect.
And at a fundamental level, they're just very different types of waves, aren't they?
Absolutely. Light waves are transverse electromagnetic waves. The oscillations of electric and magnetic fields are perpendicular to the direction the wave travels. Sound waves in air, as we established, are longitudinal mechanical waves. The oscillations, the compressions, and rarefactions are parallel to the direction the wave travels.
Okay, fundamental differences there. So, given sound is relatively slow, how do scientists actually go about measuring its speed accurately in air? What's the method?
A classic experiment involves setting up 2 points, let's call them A and B, at a known, carefully measured distance apart, say a kilometer or so. Each point needs a way to make a loud, sharp sound, maybe a small cannon or a gun firing a blank and a precise timer, like a stopwatch.
Okay, 2 stations, known distance. Then what?
An observer at Station B starts their timer when they see the flash or smoke from the gun fired at Station A. They stop the timer when they hear the sound arrive. This gives the time taken for sound to travel from A to B.
But wind could affect that, right?
Exactly. So to cancel out the effect of a steady wind, they repeat the process in the opposite direction. Fire the gun at B and time the sound's arrival at A. By averaging the time taken to travel from A to B and the time from B to A, the effect of the wind, if it's constant, is largely canceled out.
And then it's just distance divided by the average time.
Pretty much. Speed equals distance divided by time. By law and dollar, BTAVG. You use the known distance and the average time measured. Of course, as our notes point out, there are sources of error. Human reaction time in starting and stopping the stopwatch is 1.
Yeah, that personal error.
Right. And also, variations in temperature and humidity along the path the sound travels can affect the speed slightly, so it's an approximation, but a pretty good one if done carefully.
Okay, that makes sense. Now, we've spent a lot of time talking about the sounds we can hear, the sonic range. But you mentioned earlier there's a whole world of sound beyond that.
Absolutely. The typical range of human hearing is generally considered to be from about 20 hertz, on the low end, up to 20,000 hertz, or 20 kilohertz, on the high end. This is what we call the audible or sonic range. Though it's worth noting this range can vary a bit from person to person, and it often decreases, especially at the high end as we age.
We're most sensitive somewhere in the middle of that range.
Yes, human hearing tends to be most sensitive in the range of roughly 2,000 hertz to 3,000 hertz, which is important for understanding speech.
Okay, so what lies below 20 hertz?
Sounds with frequencies below 20 hertz are called infrasonic sounds, or infrasound. These are very low frequency vibrations. We generally can't hear them, though sometimes very intense infrasound might be felt as a vibration.
Do animals use infrasound?
Some do. Large animals like elephants and whales are known to produce and detect infrasonic sounds. It's thought they use these low frequencies, which can travel very long distances without losing much energy, for communication across vast areas of land or ocean.
Wow, long-distance calls using sound we can't even hear. Okay, what about the other end, above 20 kilohertz?
Sounds with frequencies exceeding 20,000 hertz, 20 kilohertz, are called ultrasonic sounds, or ultrasound. Again, these are beyond the upper limit of human hearing, but many animals have hearing ranges that extend well into the ultrasonic region.
Like dogs. We always hear about dog whistles.
Yeah, exactly. Dogs can typically hear up to 45 kilohertz or even higher. Bats are famous users of ultrasound, hearing up to maybe 100 kilohertz. Dolphins go even higher, perhaps 150 kilohertz or more.
And they use this for more than just hearing.
Oh, definitely. Bats use it for echolocation. They emit ultrasonic pulses and listen for the echoes bouncing off objects to navigate in complete darkness and hunt tiny insects. Dolphins use a similar process underwater.
It's incredible to think about these hidden soundscapes constantly surrounding us, sounds we're completely oblivious to. And ultrasonic sounds aren't just for the animal kingdom, right? We found ways to use them too.
Indeed, we have. Ultrasound has some very useful properties. Like ordinary sound, it's a wave, but because of its very high frequency, it carries significantly more energy. Also, importantly, because its wavelength is very short, ultrasound tends to travel in a much more focused directional beam. It doesn't spread out or bend around corners as easily as lower frequency sound. This is called high directivity.
Okay, high energy, very directional. So how do we put this focused, high energy sound to work? What are the applications?
Oh, they're incredibly diverse. We've basically mimicked nature in some cases. Like bat echolocation, we developed sonar sound navigation and ranging. It uses ultrasonic pulses to detect underwater objects, map the seabed, measure distances, find submarines, locate schools of fish.
So underwater seeing with sound. What else?
In industry, ultrasound is used for drilling and cutting hard, brittle materials, like glass or ceramics. It can also be used for very delicate cleaning.
Cleaning? How does that work?
You immerse the object, like intricate jewelry, watch parts, or electronic components, in a cleaning fluid and bombard it with ultrasound. The intense vibrations create microscopic bubbles that scrub surfaces clean in tiny crevices. It's also used non-destructively to detect internal flaws, cracks, or voids in metal castings or welds without having to cut them open.
And in medicine too, right? Ultrasound scans are very common.
Hugely important in medicine. Medical ultrasonography uses pulses of high-frequency sound sent into the body. The echoes that bounce back from different tissues and organs are detected and used to create real-time images.
So you can see inside the body without x-rays.
Yeah, exactly. It's used to look at soft tissues and organs, liver, kidneys, gallbladder, uterus. It's famous for monitoring fetal development during pregnancy, of course. It can detect things like gallstones, kidney stones, tumors.
And for the heart.
Yes. That's called echocardiography. It's a specialized ultrasound scan specifically to image the heart chambers, valves, and measure blood flow, assessing its function. And beyond imaging, high-intensity focused ultrasound can actually be used therapeutically for surgical purposes.
Like what?
They can be used to break up kidney stones or gallstones into tiny fragments that can then be passed out of the body more easily. It's also used in some types of eye surgery, like cataract removal.
It's truly remarkable how these sounds, completely beyond our own hearing, have become such powerful and versatile tools in so many different areas. Now, one final clarification our notes emphasize, the difference between ultrasonic and supersonic. They sound similar, but mean very different things.
Yes, that's a critical distinction and a common point of confusion. They are absolutely not the same thing. Ultrasonic, as we've just discussed, refers to the frequency of a sound wave specifically, a frequency higher than 20 kilohertz, above human hearing.
Okay, ultrasonic is about high frequency.
Right. Supersonic, on the other hand, refers to the speed of an object relative to the speed of sound in the surrounding medium, usually air. An object is traveling at supersonic speed if it's moving faster than the speed of sound, which is about 330, 340 meters in air, depending on temperature.
Like fighter jets or the old Concorde airliner.
Exactly. Those aircraft could break the sound barrier, meaning they exceeded the speed of sound traveling at supersonic velocities. This often creates a sonic boom.
So ultrasonic high-frequency sound wave, supersonic object moving faster than sound. Got it.
Completely separate concepts. One describes the wave, the other describes the object's motion.
Well, this has been an absolutely fascinating deep dive into the intricate world of sound waves. Really covered a lot of ground. We've journeyed from the fundamental vibrations that kick everything off through the absolute necessity of a medium for sound to travel, explored the differences between longitudinal and transverse waves.
And looked at all those factors that influence how fast sound actually moves the medium itself, temperature, humidity, and what doesn't affect the speed, like loudness or pitch.
Right. And the stark comparison with light speed was eye-opening. Then finishing up with those sounds beyond our perception, infrasound and ultrasound, and their incredible diverse applications, especially ultrasound.
We've definitely explored the core principles outlined in our source materials, hopefully gained a much deeper understanding of the unique nature of sound waves and how they behave all around us.
Absolutely. So, as you, our listeners, navigate your day from now on, surrounded by this constant symphony or sometimes cacophony of sounds, perhaps you'll have a newfound appreciation for these invisible waves of energy constantly interacting with your ears and the world. And here's a final thought to maybe ponder on your own. Considering how dramatically the speed of sound changes in different materials, super fast in solids, slower in liquids, much slower in gases, how might this fundamental property be cleverly leveraged or perhaps pose significant challenges in advanced technologies we haven't even discussed? Thinking about communication or detection systems designed for extreme environments, maybe, like the crushing pressures deep in the ocean, or trying to listen through the complex geological layers deep within the Earth's crust, it definitely opens up another fascinating realm to explore.